area of adaptive antennas, space-time processing, MIMO system, and cooperative communications, which is, that may be quite related to some of the research over here. So today, I think actually he has been in the UK for a few weeks, and he has been to the Queen's Belfast University under the chief sponsored by British Council, and just have some connection, some collaboration between the University of Vietnam and the UK. So I take the opportunity to invite him here. This is the State University, and luckily he can give us a talk today. So please welcome as he can tell you about the title.
Thank you very much. Good afternoon, everyone. It's my honor today to be here. And first of all, I would like to thank Dr. Nguyen for inviting me to this beautiful university. And as introduced, I'm working mainly with the adaptive antennas, MIMO communication, and also with the cooperative communication. And the topic of my talk today is about MIMO and network coding, which is the combination of the network coding with MIMO for wireless communication. The title is called Physical Layer Network Coding for Wireless Bidirectional MIMO Channel. And this is the agenda of my presentation. First is introduction, and then I would like to give some outline about the principle of network coding that is currently known as a tool to boost the network throughput. And then I would like to introduce the idea of MIMO physical layer network coding using a kind of MIMO, which is a spatial division multiplexing. Followed by the MIMO Kinsey, which is another type of MIMO called space-time block code. And I would like to draw some open research problem. So first is introduction. We probably know that network coding is an effective means to increase the network throughput. While the conventional network coding was applied to the wide network, meanwhile, wireless communication is moving from single hop communication to multi-hop related communication. Therefore, the application of network coding to wireless network is a natural approach to obtain the improved network throughput. MIMO system have been known as a tool or techniques to increase the channel capacity as well as channel quality of feeding channels. And if we combine MIMO with network coding, then we can achieve great benefit of both MIMO and network coding, so that we can increase the network throughput as well as increase the signal quality. And in this presentation, I would like to explain some ideas. The first is the difference between the network coding for wide and for wireless network. And then I would like to explain how we can perform physical layer network coding for wireless network, and how we can achieve network coding in MIMO wireless network. So first of all, what is network coding? And normally when we hear about coding, we often think that the coding is done at the source of the transmission. For example, you can see that we can use source coding to achieve the compression, the data compression, or we can use channel coding for error correction at the source. But for network coding, coding is not done at the source, but is done at the network nodes. The aim or the objective of network coding is to achieve improved network throughput, rather than like a compression ratio or error correction as in source code or channel code. For example, in this figure, we can see that we have a communication network with two end nodes and two intermediate nodes. And we often see this intermediate node as a router in the data network. So network coding will be implemented at this network node so that we can achieve improved throughput. This is an example of conventional network. In the conventional wide network, normally data is stored and forwarded at the network node. For example, when the data from network from the source S, in this case N1 to be sent to N3, and we have data from N3 to be sent to N1, then there are 4 phases of transmission. The first one is N1 send F1 to N3 by N2. And then N3 send F3 to N1 by N2. And then N2 relays F1 to N3 and relay F3 to N1. So in total, we have 4 phases of transmission. And the throughput of this network can be calculated by the total data to be transmitted to the end node divided by the total transmission time. So in this case, we have 4 phases of transmission. Then network the throughput is defined by this equation. But how we can improve the network throughput? And the possible solution is to reduce the transmission time by using network coding. So what network coding is actually? Network coding, as a definition, is a technique used to improve a network throughput, efficiency, and scalability. And instead of simply forwarding in the conventional network coding combines received packets from different sources as one packet and transmit it to the node, to the end node. And in the combined message, if we use the finite field to combine the message, then the combined message is of the same length as with the message received from source node. So we can have a combined message, which is a combination of all the messages from all the source node. And the original message can be recovered as single as a destination by using, for example, Gaussian elimination. This is an example of very simple network coding, which is called linear network coding. In this linear network coding, we also assume that there are 3 nodes with 2 hops transmission. So the combination at the relay or the intermediate node in this case can be done by using modulo 2 or XOR operation. Then we have F1 is a frame or packet transmitted from N1, and F3 is a packet transmitted from N3. Then the compiled packet at the relay F2 will be F1 XOR F3. So here we can see that because at the relay we can achieve the combined packet F2, then we can send F2 simultaneously to N1 and N3. Or we can say that we broadcast the F2 to N1 and N3. So by using this combination packet and broadcast, we can see that we only need 1, 2, and 3 phases of transmission. So we can reduce 1 phase of transmission. And as a result, we can improve the network throughput. For example, this compare the operation of store and forward network with network coding. We can see in the conventional store and forward network, we need 4 phases of transmission, while in the network coding network, we only need 3 phases of transmission. So basically, we can increase the throughput by nearly 25%. So what is the motivation for using network coding in wireless network? We know that wireless network are moving from single hop to multiple hop relay transmission. For example, we can see that in the current wireless network, such as the ad hoc network, wireless wireless sensor network, WiMAX network, or even the 4G, the mobile communication network, in the standard of LTE Advanced. All of these networks have adopted relay the transmission or relay communication. And this is an example of wireless ad hoc network or wireless sensor network. You can see that there are many relay nodes between the end nodes. So the network can use relay nodes to relay the message between the end nodes. Similarly, we can see in the satellite communication, in this case we can see that the satellite transponder is working as a relay to relay the message between the earth station. Or even in LTE or WiMAX network, they also define different type of relay nodes. For example, this is in LTE Advanced, they define two type of relay nodes. This is the first type called Taiwan, and this is type 2. For Taiwan, they use a relay node here or relay station here to extend the coverage of the network. In this case, they can use a relay node not to extend the coverage, but to increase the signal quality by the type of corporate coverage communication, because they can provide two. One is a direct link, and the other is a corporate coverage link by the relay node or relay station here. And in WiMAX, they call this Taiwan and Type 2 relay station as a transparent or transparent relay node. And if we classify the relay node, there will be two main type of relay network. The first one is called unidirectional relay network, or we often know it as a one-way relay network. And in one-way relay network, the uplink and downlink transmission in this way is not consecutively, alternatively. For example, when the downlink from E node B to UE, then the first will be sent from E node B to relay station, and then from relay station to UE. And for the uplink, would be UE to the relay station, and from relay station to the E node B. And this operation is similar to the start and forward wire network, and it also requires 4-phase of transmission. But for the second type of relay network called bidirectional or two-way relay network. In this network, the downlink transmission and uplink transmission can be done simultaneously. For example, E node B and UE can simultaneously transmit to the relay node. And in the second phase, the relay node can broadcast the combined message from E node B and UE to the UE and to E node B. So basically, in this scenario, there are only two phases of transmission, and we can set the transmission time, and then we can increase the network throughput further, because compared to the wire network, we only need two phases of transmission. So how we can apply network coding for wireless network? Possibly, we can apply network coding to wireless relay network at the network level, similar to the wire network. But in the case of wireless network, there are some challenges. And the first one is the wireless channel broadcast in nature. That means if we do not transmit at the same time, there will be co-channel interference. And because of this co-channel interference, we need to cope with the co-channel interference to estimate the transmit the signal from the node. So we need to use signal processing to cancel the co-channel interference. However, the broadcast nature of the channel, wireless channel, can be exploited to improve the network throughput. That means co-channel interference channel can be exploited, and we can achieve better network throughput. And here's an example of the Y network, and this is the wireless network. For Y network, we can see that there is no interface. But for the wireless ad hoc network, if these two networks transmit at the same time, and of course at the same frequency, there will be co-channel interface at the network terminal. And how we can do network coding for wireless ad hoc network? As I mentioned before, network coding can be applied at the packet level, or also known as at the MAC level, similar to the Y network. But in this way, we still need 3 phases of transmission, so no advantage compared to the Y network. But if we exploit the broadcast nature of the wireless channel, then network coding can be applied at the physical layer, not at the packet layer, network layer, but at the physical layer. And then we will have physical layer network coding called PNC. And in this case, PNC can help to increase further network throughput, like I mentioned before in the case of the bidirectional relay network in LTE bands. Here, for example, if we apply network coding at the layer 3, that is packet level layer, then we need 3 phases of transmission. But if we apply the physical layer network coding, then there will only 2 phases of transmission. One is called multiple access phase, the other is the broadcast phase. So in this case, we can see clearly that physical layer network coding can help us to increase further network throughput. And principle of the physical layer network coding. So for network coding at physical layer, we should do at a symbol level, a bit level. So in the case symbol level, N1 send transmitted S1T, and N3 transmit S2T. So in this case, we have the transmitting S1T and S3T. And network coding will be applied directly to this signal. So at the relay node, the first relay node will detect or will receive the combined signal S1, S3, and have R2T signal. And this is the in-phase component, this is quadrature component. So we have A2, A3. And from this combined A1, A3, and B1, B3, we need to do a PNC mapping so that we obtain A2 and B2 as an in-phase quadrature phase for the combined signal. This is a network code signal. S23, S2T is called network coded signal. The network coded signal will be in this form. While A2 is an in-phase component and B2 is a quadrature component. And this signal will be broadcast to N1 and N3. But how we can do the PNC mapping here? Here's an example of the PNC mapping for the in-phase component only. And the mapping for the quadrature component is quite similar. For example, if we have S1 in phase, S3 in phase, so the combination will be 1, 1, 0, 1, 1, 0, and 0, 0. If we convert to a symbol, we will have 1, 1, minus 1, and 1, minus 1, minus 1, minus 1. And the combine A1 plus A3, which is a combination A1, A3 will be 2, 0, 2, 0. The same we will have 2 and minus 2. And the difference will be first 0, 0. And the mapping, PNC mapping will be 2 and minus 2 will be mapped to minus 1. And 0 will be mapped to 1. And we have the PNC mapping at the symbol level. And how's different between network coding and physical layer network coding? You can see this is a network coding domain, this is a physical layer domain. So if we do network coding, we need to have the packet, and then we combine it together. F1 and F, and for example, this Fi, J, we have Fk combined at the packet level. But if we do it at the physical layer, we can combine symbol Si with symbol Sj to have the symbol Sk. how's the performance of physical layer network coding compared to the network coding? Here's the simulation result, the bit error simulation result for BPSK modulation. And we can see here, for the case using network coding and for the case using PNC, the physical layer network coding, there is a little bit decrease in video performance when using physical layer network coding. And this is due to the interchannel, that is co-channel interference. But we should note that although there is some small decrease in bit error performance, PNC can increase the throughput by nearly 1/3 compared to the using network coding. So the advantages is much more than this more some loss in the bit error performance. How we can do PNC for MIMO channel? So what is MIMO? You probably know that MIMO stands for multiple input and multiple output. Actually, it is a wireless system that uses multiple antennas at both transmitter and receiver. For example, here is an example of MIMO transmission system, where transmitter has 2 antennas and receiver also has 2 antennas. It's a channel between these 2 transmitter and receiver. We can see that multiple input and multiple output. That's why they call it MIMO channel. And why we use MIMO? Because MIMO provides a lot of advantages, such as increased channel capacity, increasing the system performance, and also increase the security of the system for some cases. And classification MIMO system. MIMO system can be classified into 3 main categories. The first one is called spatial activation multiplexing, normally abbreviated as the SDM. The objective of SDM, MIMO SDM, is to achieve multiplexing gain so that we can increase the stretching efficiency, that is the throughput of the system. The second type is space-time coding, normally called SDC. The objective of it is to achieve diversity gain so that we can increase the signal reliability, and that is, we can reduce bit error. The third one is pre-coding, also known as beamforming, is used to increase the stretching efficiency. But the advantage of pre-coding is that it requires the channel knowledge so that it can form the pre-coding metric. So in the following, I will introduce 2 MIMO schemes which use PNC. The first one uses SDM, the second one uses space-time coding. Why we need to apply PNC to MIMO? Because as I explained before, if we combine MIMO with PNC, we can achieve the advantages of both MIMO and PNC. The second reason is that MIMO is already included in the current wireless standards, such as LTE, LTE Advanced, Wi-Fi, WiMAX, etc. Then, as I mentioned before, there are 2 different combinations, MIMO and PNC. The one combined with the SDM is called MIMO SDM PNC. The other is called MIMO SDBC PNC, that the case of using space-time block code. Here's an example of MIMO SDM using linear detection to estimate the signal. So in this system, I assume that the system uses 2 antennas, both the node and 1 and 2, and use 4 antennas at the relay nodes so that the linear detection can be easily performed. And all nodes, that is N1, N2, and also relay node, use SDM for transmission. That is, transmit the signal parallel transmit stream. For example, N1 will send 2 streams, X1, X2. N2 also send is 2 streams, X1, X2. And relay also transmit 4 parallel streams. So in this system, because the two anodes transmit two streams in parallel. So it can provide double multiplexing gain compared to the case of using only single antenna. And because in the physical layer coding, we will use two-phase transmission. So in the first phase, here, the two anode N1 and N2 will transmit at the same time. The vector transmit vector X1 and X2. X1 from N1, X2 from N2. So at the relay, we will have the relay signal that is in the form of system equation R equal to 1 over square root of 2 H multiplied by X plus 10. Here, H is a channel, and X is the transmit vector, and that is the noise vector as a relay. So how we can map this receive signal as a relay to the network coded symbol in the form of X1 XOR with the X11 XOR with X12, X21, and X12 XOR with X22. The principle is as follows. Because we need to have the network code symbol in this kind of this form. X as a relay 1 equal to X11 XOR X21, and X2 equal to X12 XOR X22. And there is a method, two methods for this mapping. One is called likelihood ratio, and the other called is selective combining for mapping the symbol to the network coded symbol. This can be done if we have X11 plus X21 and X11 minus X21. That is, if we can have the sum and different symbol from two network nodes, from N1 and 2. That means we have X11 plus X21 and X11 minus X21. Then we can map it to the first network coded symbol. And similarly, if we can have the sum and different version of the signal X12 and X22 here in the blue color, then we can map it to the second network coded symbol, XI2. But how we can estimate this sum and different symbols? This is very simple. If we, from this system equation, if we use a special metric called sum and different metric, U, that is in this, illustrated in this form. Then we have U minus 1 and U here, which is a unit identity metric. So then we will have the system equation will be given by this, multiplied by this. And we denote this by H tilde, and this one by X tilde. And because of the U is illustrated in this form, then we will have X tilde is given by this one, which is in the desired form, which give us the sum and different symbol. So from this equation, we can apply linear estimation to X tilde to get the estimation of the sum and different symbols. And how we can achieve by using linear estimation? We can use combining matrix G. G will be given by this equation if we use minimum mean square error estimation, and will be given by this if we use zero forcing estimation. So when we multiply the received signal as a relay with G, we will have the estimated vector, which is comprised of sum and difference of the transmitted symbol from the anodes. And by using the likelihood ratio, we can calculate the likelihood ratio given by this equation. And from here, we can decide the first network coded symbol, XI1, by comparing the likelihood ratio with the threshold 1. And similar, we can design the second network code symbol XR2 by similar method. Another way for mapping is to use the selection combining. For selection combining, we just do very simple decision, where GG11 here is the first output from this matrix, and 33 is the 3 output. This is the first diagonal element. This is third diagonal element of the G and G, the H matrix. And similar for the second network code symbol. And in the second phase, that is a broadcast phase, the relay will transmit to network code symbol, that's XR1, XR2 to the end node. Then at the end node, we will receive at node N1, we will receive U1, and node N2, we will receive U2. And because we have 4 transmit antennas to relay, we can select 2 antennas randomly for transmission. And in order to estimate the transmitted symbol at the node 1, we will use similar linear estimation using either zero forcing or MMSE. And by using combining matrix G1 combined with the receive second vector U1, we can receive X hat R1. And similar for X hat R2. And because node 1 will need to receive the symbol from node 2. But here, node 1 receives only the estimated symbol of the network coded symbol. So in order to recover the transmit symbol from node 2, it will do the XOR of the estimated network coded symbol with its transmitted symbol, X1. So it will then receive X hat 2, that is the transmitted vector from node 1. Similarly, node 2 can estimate the transmitted symbol from node 1, that is X1 by XOR, the estimated symbol, network coded symbol XR1 with its transmitted X2. Then you can receive the transmit vector from the other node. And this is performance, with the error performance of the MIMO PNC using zero forcing. And here we illustrate 7 results using like ratio as well as selective combining. And for the case of we compare with the case of this is paired with the reference number 4 here. That is actually this is a SIMO PNC, non-MIMO, and also similar for this one. This red line is also this is a SIMO actually. They call it MIMO, but actually it's a SIMO in number of reference number 4. Then our proposed MIMO SDN has the same diversity order with the SIMO PNC system, but we lose some SNR for about 2.4 dB in SNR. But our system can provide double multiplexing gain because we use 2 antennas in the end node. While this reference use only 1 antenna at the end nodes, so they don't have any multiplexing gain, while our system can provide double multiplexing gain, that is, our transmit throughput is double. But if we use MMSE estimation, we can achieve similar media rate performance, while still have double multiplexing gain when compared